Today I'm showing how to model and simulate a water flow control process with a data-driven approach. There is a real data measurement on the left side and a simulated data from a model on the right side. In this example, there is a controller and it's called a closed loop control. In this other example, there is no controller and it's called a open loop control. And in this video we'll show how to go from here to here. The flow process control is as follows. The water begins at the tank, then it is pushed into the system by the pump. It goes through the flow meter, which measures the flow in liters per minute or gallons per minute. Then it goes through the venturi tube, which internally creates a pressure drop so that the differential pressure sensor can calculate the water flow by using Bernoulli's equation. Then it goes through a control glove valve, which proportionally allows or blocks the liquid flow. Then it goes into the column, which is used for accumulating water and displaying the liquid level in centimeters or inches with this ruler over here. It is also used for fluid level control processes. Also, the column contains two outlets on the bottom that drop the water into the tank by gravity and one at the top for the water overflow. So the flow process looks like this. And back into the tank by gravity. Also from the water overflow back into the tank. The three most important variables that I will be talking about throughout this video are SP, which is short for set point, which is the desired flow that the operator wants to set. It can be input from the HMI, human machine interface over here, by sending a signal directly to the PLC, programmable logic computer over here, or by sending data through the cloud, the internet over here. PV is short for process variable, which in this case is the measured water flow. The reading should be the same between the flow meter and the sensor. In fact, the flow meter is used as a reference instrument to calibrate the sensor. And finally, CV, short for control variable, which is the aperture of the glove control valve. In a nutshell, the brain of the system, the PLC, manipulates CV to change PV so that PV matches the desired SP value. The machine is located in Peru while I'm located in Germany. To remotely interact with the machine and other purposes, I've developed an application named Monoxware. In other words, I put the machine in the cloud. I will be interacting with the following modules. In the AC drive module, we can turn on the pump and change the speed from 0 to 60 Hz. In the live streaming module, we can visualize the level measurement as well as the flow measurement. In the hard device module, we can configure the sensor. Everything is already set up and we can visualize PV's value in terms of liters per minute. In the process values module, we can set up the mode of operation and interact with the process variables. Manual mode means open loop control. Auto mode means closed loop control. In the PID control, module, we can set up the values of the proportional, integrative, and derivative gain, so that the PLC can control the flow process. In the trends module, we can visualize in real time the values of SP, PV, and CV from 0 to 100%. Most importantly, here is where I can do the data acquisition by pausing the live refresh, then hitting the save icon and saving the data as a CSV file. All of the files you see here are previous data acquisition from this process, which I have used for different tests. Now we can proceed to build a mathematical model by using only data acquisition. This is called a data-driven model. This ends the quick Monoxware introduction, and now we move on to the model building process with Matlab and Simulink. This is Matlab System Identification application. It uses experimental data to create mathematical models. On the left side, we have two data acquisitions displayed as follows. U1 is the input, which is the CV, while Y1 is the output, which is PV. This is a CV versus PV graph. For both acquisitions, I am sending square signals to the CV in the range of 40 to 80 and omitting the other ranges. The reason is the behavior of the glove valve and the system linearity. This graph represents the glove valve's aperture versus the corresponding water flow. At 0%, the valve is completely open, while at 100%, the valve is completely closed. From 0% to 30%, there is almost no variation at all. The data shows it is saturated around 92%, rather than 100%, simply because I did the measurements with a pump speed lower than the speed that was used when the sensor was calibrated. From 40 to 80%, this range, there is the most of the variation, and again from 80% onwards, the process has no variation, also showing a bit of under 0% because the increased pressure when the valve is completely closed. For this reason, the range 40 to 80 is the most suitable for the data acquisition process. Once a proper acquisition is made, we can proceed to create the model. The method I found most suitable for this process is the process model method, which will create a transfer function. Using the following settings and hitting estimate produces a model with a 82.58% fit. With more individual parameter fine-tuning, I was able to get this previous model, which has an 88% fit for one of the data acquisitions, and a 86.75% fit for the other acquisition. By right-clicking the model, we can explore its properties, coefficients, and so on. Now we export this model to the workspace so that we can use it in Simulink. Here we have the same model but with two control options. The upper one represents the closed loop version and the bottom one represents the open loop version. All blocks are color-coded. They also contain a descriptive name and should be easily understood. The data-driven identified plant block contains the model that we saved to the workspace. The real-time synchronization block allows my laptop to run their simulation in real time so that I can compare both the real process and the simulation process in real time for this video. On the left side of the screen, I'm going to set up the live real process with Monoxware, while on the right side of the screen, I'm going to set up the live simulated process with Simulink. Now that everything is ready, I can proceed to test arbitrary values such as 60, 40, 80, 30, 50. The open loop test is quite satisfactory and the data matches around 87%. Now I proceed to demonstrate the closed loop. Proportional and integral controller has been set up with the following values: a proportional gain of this and an integral gain of this. We can proceed to compare different arbitrary values: 40, 80, 30, From the previous test that I have done, there should be a match of about 80% between the process values. As a second example, we will tune the PI strategy so that the overshoot is eliminated. We open the PID AutoTuner app and we move the response time slider to the left to make the controller slower. Right about there. And we move the transient behavior slider to the right to make it more robust. right about there. Now by clicking on Show Parameters, we can compare the previous ones and the current ones. We can see some important stuff like the rise time, settling time, and so on. We update the block, close this, and now we have the new values, which we can introduce here. And again, we can test and compare. And so on. We have observed that a data-driven model can replicate a real process with a match of about 80 to 87%. Thank you for watching.